Today, we're going to talk about Chapter 26 and about AC electricity. Now, AC stands for alternating current. And most of what we've been talking about so far has been DC, or direct current. And so in direct current, the electricity always flows in one direction. Whereas in alternating current, the electricity wiggles back and forth. Everything we've been learning about so far has been DC. Our battery always had the same orientation. We didn't have like a battery flipping back and forth or something like that. It always had the same orientation, so we called that DC, or direct current. We're going to start talking about alternating current, and alternating current circuits can be super tricky. It's really a very complex topic, and we're just going to scratch the surface. So this is one topic that we're just going to kind of talk a little bit about. I want to focus on three things. First of all, what is AC, and why is it useful? And transformers are a big part of why it's so useful. And then I want to talk just a little bit about household electricity, because it turns out that the electricity in your household is AC, it is not DC. And then finally in this chapter, I want to talk just a tiny bit about electrical safety. That's the goal. So let's jump right in. Here we see a picture of three birds on a wire, and this might be a high-tension power line. And maybe you've seen birds on power lines before and thought, how come they don't get zapped? The reason is because, remember, it is a potential difference that drives a current, not a potential. And so these birds are sitting on this transmission line. It might even be at, I don't know, 7,000 volts if this is in a city. It might be at 750,000 volts if this was a transmission line between cities, or between a power plant and a city. Why don't they get zapped? Because their entire body is at 750,000 volts. And so there's no potential difference to drive that current. Okay. So it is an alternating current, which means that the EMF switches. You know, if positive is on top, then it switches and positive's on the bottom, and then back and forth and back and forth. That's why we call it alternating current. And so, of course, we can use a cosine or a sine to write that. And so what we're doing here is we're just using a cosine function to represent the EMF. And so this is just a wiggly function, and it alternates between positive E naught and negative E naught. And this is indeed what the household electricity, what the electricity in your house does. For your household electricity, these peaks are at about 170 volts, and the negative peaks are about negative 170 volts. We're going to come back to that in just a minute. Recall that period is the amount of time for one complete oscillation, and that frequency is the inverse of period. And so here we see a graph of EMF versus time, and of course, one period is the amount of time for one complete oscillation. Do be careful, your calculator does need to be in radian mode here because of this 2 pi here. Okay, so we can talk about the average current, but we can also talk about the instantaneous current. And both of those ideas are useful when we're talking about alternating circuits. And so we're going to use this convention that the instantaneous voltage will use a little v, and the max voltage will use a capital V for. Similarly with current, instantaneous current we will use a little I, and peak current we will use a big I. The nice thing is that a lot of the equations, basically all of the equations we learned for DC circuits, apply for AC circuits as well. We just have to be a little bit careful. Ohm's law applies at any instant, where the instantaneous voltage is equal to the instantaneous current times the resistance. Now, of course, we don't need to have an instantaneous versus average resistance, because the resistance just is, right? The resistance of an object just is whatever it is, whether I hook it up into an AC circuit, a DC circuit, or no circuit at all. And so since we can write the voltage in this way across a resistor, then we can write the current in this way. Again, notice here the instantaneous current is just the peak current times some wiggly function. Again, the 2 pi reminds us we need to be in radian mode. So we could plot these and kind of help us to visualize just a little bit. The instantaneous current goes like this, and the voltage goes like this. Notice they are in phase, and this is across a resistor. So if we apply a voltage across a resistor, then we get a current. As the voltage varies, the current varies. That seems fairly easy to believe. The current is at its maximum and minimum when the voltage is at the maximum and minimum values also. That means, to use some language from earlier in the semester, right, that means that they are in phase. Now, that's not always the case. It might seem obvious that it should be, but it's not always the case. If you have capacitors or a element called an inductor, and an inductor is just a coil of wire, in both of those situations, the voltage and the current are not in phase. We're actually not going to delve into those in this this semester. It's very interesting stuff, but we just have to pick and choose, so we're going to skip those topics. Okay, so recall that in a DC circuit, the power is given by I squared R, or V squared over R, or of course I times V. And as long as we work with what we call RMS, or root mean square voltages and currents, all the expressions for DC power that we learned will work for AC power. Now, what is this thing RMS? Well, if we wanted to just say intuitively what does the RMS value mean, what it means is it's kind of like an average. But let's talk about how we need something a little bit more sophisticated, about why we need something just a bit more sophisticated than just an average. So let's say that I have an alternating current coming out of, or excuse me, an alternating voltage coming out of my outlet in my wall. And so we might be plotting EMF versus time. And so we could graph this. It's going to wiggle. It's going to look like a sine curve, something like this. And it would just keep on going, right? And we say, okay, well, what is the average value of this sine curve? Well, notice that we have just as much above as we have below. Right? And so what is the average value of this? Well, the average is simply 0. But gosh, that's not really that interesting, right? It's only 0 for brief moments. Calling, the average being 0, that's just not that interesting. We need a better idea. Because it is delivering current. It is delivering power. I can run my toaster off of it. So clearly something is happening. An average of 0 is clearly not that informative. So we introduce the idea of a root mean square. And how we do it is we take it in opposite order. First, we square the data. Well, what happens if you square a sine function? Oh, it looks something like this, or a cosine function. It looks something like this. Okay, now, can we take an average of that and get something that makes sense? Yes, we can. So this is when we squared it. And now we are going to take an average, or a mean. So it is the root mean square. So now I'm going to take a mean of this, and it might be something like this. And then what do? We take a square, or to be precise, we take the square root of that number, which ends up being something like this. And so we end up with some reasonable number that we can use to calculate things like power, to calculate things like power. And more power. So to calculate things like, specifically, power. It gives us a number, a positive number that isn't 0. It makes sense. Now, on the slide here, we can see our relationships between the RMS value and the peak value. And so some of you might have heard me earlier say that in a household circuit, this peak EMF here is about 170, and the peak down here would be about negative 170. There may have been some of you that said, wait a minute, aren't household outlets 120 volts? The answer is yes. If we're talking about AC circuits, and we give you a voltage or a current without specifying RMS, peak, average, then what we mean is RMS. So when you say, oh, my household outlet is at 120 volts, that is the RMS value of the EMF coming out of that circuit. And again, the RMS and the peak values are related by this square root of 2. And so, again, we can just use these same equations that we learned for DC as long as we promise to use the RMS values. So, let's do a quick example, and I'll just really quick erase my board. All right, so we have a hot wire in a toaster dissipating 580 watts when plugged into a 120 volt outlet. What is the wire's resistance? Now, let's be clear here. This 580 watts is not an RMS value. It just is, right? The power is always positive, so we don't have to worry about an RMS value. And so what that is it's really an average over some period of time. When plugged into a 120 volt outlet, the 120 volts there, since I did not specify, we must assume that the 120 volts is an RMS value. And so it says, what is the wire's resistance? Well, I'm going to use this version of our power equation. Power equals V RMS squared over R. And so then I can solve that for R. And I guess we are working on part A. So now I can solve this for R, and I get R equals V squared over P. And I guess I should specify that this is still RMS. Well, so this would be 120 volts squared divided by 580 watts. And that equals 25 ohms. Okay, part B. B says, what are the RMS and peak currents through the wire? Okay, well, for this one, we do know the voltage and the power. So I could just use the other version of this, where I go power equals I RMS times V RMS. And of course, then I can solve this for I RMS. Which is just my power over V RMS. And so now, again, I can plug in my numbers. $580 watts divided by 120 volts gives me 4.8 amps. And so that is the RMS, right? Because I used the power equation here. Now, we know that the peak value is simply the square root of 2 times that. So I peak, I think we and so there we get 6.8 amps. And finally, what is the peak voltage in a 120 volt outlet? Let me see here. I think I need to... No, looks like we can still see that a little bit. Peak voltage is going to be... Again, we're going to interpret that 120 volts as the RMS value. And so we get V peak equals 120 volts times the square root of 2, which is 170 volts. All right,